Cauchy's theorem. The statement says if f of z is analytic at all points inside and on a simple closed curve C, then integral f of z dz over a closed curve C is equal to 0. So here there are some of the basic things you should know here. So simple closed curve means it is simply connected, continuous. Continuous means there should not be any break in the curve, and non-self intersecting curves. So the first curve is simply connected and it is continuous, that is there is no break in the curve, and it is not intersected at any point. So first curve is simple closed curve and R is the region bounded by the curve. But whereas the second curves, second, third and fourth curves are self-intersected. They are intersected at some points. So it is not a simple closed curve. So to prove this theorem, we need Green's theorem. So Green's theorem says that along the simple closed curve C, so integral m dx plus n dy along the simple closed curve C is equal to double integral del m by del y minus del n by del x dx dy along the surface S. So what we do in Green's theorem is a line integral is converted into a surface integral. So that is integral m dx plus n dy over a closed curve C will be equal to double integral del m by del y minus del n by del x into dx dy over a surface. So this is the statement of Green's theorem. So now to prove Cauchy's theorem, we are going to use this Green's theorem. Now let us prove this Cauchy's theorem. As the statement says, f of z is analytic at all points inside and on a simple closed curve C. So now let us take a simple closed curve C. So f of z is analytic at all points inside and on a simple closed curve C. So there are infinite number of points on a curve and also inside the closed curve. So f of z is analytic at each and every points which lies on the closed curve C as well as inside the closed curve C. So f of z, so let f of z is analytic at all points inside and on a simple closed curve C. So since f of z is an analytic function, we can write f of z as u plus iv, where u and v are functions of x and y, and z is a complex number, z equals x plus iy. So we can write, differentiating with respect to x, we can write dz by dx equals dx by dx, that is 1 plus I into dy by dx. So multiplying dx on both sides, we get dz equals dx plus I into dy. So now we have to prove this result, integral f of z dz over a closed curve C is equal to 0. So then integral f of z dz over a closed curve C equals integral f of z is u plus iv and dz is dx plus I into dy. So on simplifying further, we get u dx plus I into u dy plus I into v dx plus I square into v dy. So separating real and imaginary parts, u dx minus v dy, that is I square is minus 1. So u dx minus v into dy plus from second and third term I is common. So v dx plus u dy. So now to simplify further, we have to use Green's theorem. So let us take the first term as m, second term is n. So here also the same thing, first term is m, second term is n. Now to solve this equation 1, we use Green's theorem. So by Green's theorem, if R is the region bounded by C, so if you see the figure, so this is the region R which is bounded by C. So we have integral m dx plus n dy over a closed curve C is equal to double integral del m by del y minus del n by del x into dy dx. So now we use Green's theorem to solve equation 1. So now equation 1 is integral f of z dz over C equals integral u dx minus v dy plus I into integral v dx plus u dy. So this is equation 1. So here in the first integral, take m equals u and n is equal to minus v, and from the second integral m is v and n is u. So we have to find del m by del y minus del n by del x. So integral f of z dz over C equals, now applying Green's theorem, so line integral becomes surface integral. So double integral, so m is u, so del m by del y is del u by del y and n is minus v, so minus del n by del x equals minus of minus becomes plus del v by del x plus del v by del x of dy dx plus, now for the second integral, so double integral m is v, we have to find del m by del y. So del m by del y becomes del v by del y, then n is u, so minus del n by del x is minus del u by del x of dy by dx. So now, f of z is analytic. So we know that since f of z is analytic, it satisfies CR equation. So since f of z is analytic by CR equation, we have ux equals vy and uy equals minus vx. Now we are going to use these two conditions in the above two integrals. So therefore integral f of z dz over c equals double integral. So del u by del y from the second condition, del u by del y is minus del v by del x. So minus del v by del x plus del v by del x of dy dx plus double integral. So now del v by del y from the first condition, del v by del y is del u by del x. Del v by del y is del u by del x. So del u by del x minus del u by del x of dy dx. So therefore integral f of z dz over c equals, so minus del v by del x plus del v by del x becomes 0 plus I into del u by del x minus del u by del x becomes 0. We also have to take I. So therefore integral f of z dz over c equals 0. Hence the theorem is proved. So there is one more standard result here. We call it as corollary. So it states that if C1 and C2 are two simple closed curves such that C2 lies entirely within C1. So let us write a figure for this. So this is the external curve. Let us take this as C1. So C2 is the curve inside C1. So C1 is the external curve and C2 is the internal curve, where C2 lies entirely within C1. Let f of z is analytic on C1 and C2 and in the region bounded by the curves C1 and C2. So it means f of z is a function which is differentiable at each and every points which lies on C1 and C2, and also it is differentiable at each and every point which lies in the region bounded by the two curves C1 and C2. If this is the case, then integral f of z dz over C1 equals integral f of z dz over C2. So now we are going to use this result to prove the next theorem.